Okay, so today is our great pleasure to have Professor Yin Sun to give us a talk. So Yin now is an assistant professor in the Department of Electrical Engineering at Penn State University. So her research interests now focus on the statistical signal processing and optimization algorithm and also machine learning. So she has received a few best paper awards, including this 2020 IEEE Signal Processing Society Young Author Best Paper Award. So today, she's going to talk about the decentralized optimization for statistical learning over the network. Welcome.
Thank you very much for the invitation and nice introduction. And it's my pleasure to give a talk in the Math Department of RPI. Today, I'm going to talk about decentralized optimization for statistical learning over networks and share with you some of our recent research results. So first of all, let me set up a bit ground for the talk. So first of all, by statistical machine learning, we mean we would like to make predictions from statistical representative data. Say some of the applications is the following. For example, given the data set that is an image, we would like to predict what is the object contained in the image and as well as its position. And another application would be, given the data set being a video clip, we would like to predict or associate a caption to the video, and this is the video captioning application. And another example would be a Google Assistant application. So the input would be an episode of the play of a song, and we would like to predict the name of the song. And this one is a pretty popular application nowadays. It's a reinforcement learning problem. So basically, we would like to predict what is our best action in the current step, given all the observations that has been played in the past. So for all of these problems, they can be somehow abstracted as the following prototypical learning problem. So we are given a data set that consists of a pair. So here I'm more focused on a supervised learning problem. So we have a data set that consists of a pair with an input, say it's an image, and an output, which is a label of the image. And here the image is as follows, and the label is a cat. And then we input this data set to a machine, and this machine basically runs an algorithm and generate a model that is mathematically characterized as a function that can take an input, say an image, and then generate a prediction about its label. And if the prediction is accurate, say if the input image is a cat and the prediction is a cat, then we say the model is a pretty good model that that gives a good characterization of the data set. Nowadays, in many applications, however, our data set is not co-located at a single place, but in this kind of applications, they are distributed over a network. Say, for example, we have a sensor network, and these sensors are collecting data locally from their geographical locations. And another scenario would be an autonomous driving application where we have a network consists of all these autonomous cars, and they may take their own measurements, say, for example, the image of a stop sign at different states. Other applications can be a network formed by different cell phones, and for each cell phone user, they have their local data sets, say their health record and so on. So in all these applications, the data sets are not stored in a single place. However, we still would like to make predictions from this data set using all of the data sets in the network. So the problem is, how can we solve this question? A very natural and maybe a naive solution that we may think of is try to move all the data sets into a single place, and then we can leverage our traditional centralized learning algorithm to learn the statistical model. However, when the network size is huge or we have a huge amount of data, this is not very feasible because moving the data to a single place that can essentially generate a heavy traffic load to the communication system. And also, even if we can move the data to a single place, centralized processing of this data is going to generate a heavy computation burden to the centralized processing units. And more importantly, out of privacy concerns and so on, the users may not want to share their local data sets because that contains some sensitive information about themselves. So they may not even want to collaborate. So given all these difficulties, our approach is that can we design an algorithm that allows the data to stay as where they are, but we let the learning process or we let the machine learning process happening at the level of the network. In other words, we would like to to develop a decentralized learning algorithm that can allow the users to maintain their data locally. So the goal of this decentralized algorithm is to learn as if this data were stored at one place. In other words, we would like to achieve the same performance as a centralized algorithm in terms of both the accuracy and also the speed. Okay, so this is the general problem that we are interested in, and it poses several challenges in terms of algorithmic design. First of all, nowadays our data set is pretty complicated, and in order to model the data set, we may develop complex models such as deep neural nets. And in order to train these models, essentially the learning problem or the optimization problem that I'm going to talk about later on will be essentially non-convex and possibly also non-smooth. And this type of problem is generally hard to handle, even in the centralized setting. And also another challenge it will arise from the data aspect because nowadays we may have a massive network data size, and that would pose computation demand on both the local processing unit, and also it's going to generate a heavy communication load. Even if we're saying that let's not transmit the data, but keeping the data local to the users themselves, the message passing or generally sharing kind of essential information so as to enable the learning happening in the network, that is also going to generate a heavy communication load. And in order to address this problem, so this our target is to address these two challenges, and this sets up the research agenda. And essentially, it can be characterized. It contains two levels. First of all, it's a kind of feasibility problem, meaning that we would like to design an algorithm that is able to handle these two problems. And then after we have a kind of feasible problem, the next question is, can we kind of, among all these feasible algorithms, can we kind of select the best one that has the best performance guarantee in terms of both convergence rate, meaning how fast the algorithm computes a stationary or optimal solution, and also in terms of accuracy, meaning how close the optimal solution is to the ground truth that we are really interested in. Okay, so and in order to answer these two questions, and today I'm going to divide my talk into three parts. First of all, I will introduce the mathematical model of this collaborative learning problem, and then I will introduce our algorithm, basically solving a class of the collaborative statistical learning problem over the network. And finally, I will connect the algorithm to its background, meaning that our algorithm is really designed to solve a statistical learning problem. So put the algorithm into the statistical perspective, and let's discuss its what kind of properties it has. Okay, so let's start with real business. So this is the mathematical model that we are going to talk about today. So we model the full data size as a realization of a pair of random variables, where the x random variable represents the input and the y random variable represents the output. And in the decentralized setting, so the full data set is not collocated, but is partitioned among M agents, and these M agents forms a network that is modeled as a graph. So each of these nodes represents one agent, and we have these edges represents the communication link between the agents. Now, our goal is to learn a statistical model that is characterized by a function, and this is a parametric model. So the function is parameterized by a parameter theta. And this function takes an input x and generates a prediction h theta of x. And our goal is to find the best theta within the parameter space that can generate as accurate a prediction as accurate as possible. So we would like our prediction to be as close as possible to the output y. And in order to measure the goodness of the model, we associate a loss function L to the problem that basically measures the mismatch between the prediction and the label. And this gives us our loss function, that is the average of this the mismatch between the prediction and the label. So and at this point, each of these agents, they have their local data sets. So that basically defines the local loss function, and that is the average of the loss functions over the local data sets. And our goal is actually to minimize the average of the loss functions over the entire data sets in the network. And that gives our objective, the first term of our objective. And this is also a very commonly seen objective, the so-called empirical risk function. And for certain applications, we are also interested in imposing some of the properties of the solution. For example, a sparse solution. And in this case, we will attach a regularizer to the loss function. And this regularizer basically promotes the properties that we are in favor of. Say some of the possibilities could be the L1 norm or so on. And let me give a very quick and prototypical example of this problem. So we consider here a very simple case. The input data set is two-dimensional, is a two-dimensional point as plotted here. And we would like to predict the y-axis as a quadratic function of the x-axis. Okay. And the model that we are going to learn takes the following form. So our prediction function is a quadratic function in terms of the x-axis. And the loss function we associate to this problem is the simple quadratic loss function. So for each of these agents, they locally own a portion of these data sets. And if each of these agents only minimize the least squares loss between the prediction and its label, then they are going to generate different fitting functions. However, we can see that the local distribution of this data in this simple example does not really characterize the entire data set in the network. And because of this limitation, these agents cannot really learn a very good model that characterizes the entire data sets in the network. So instead of letting the agents minimizing their own local loss function, what we would like to do is to let them minimize the average of the loss functions over the entire data set, and that gives us the loss function, which is the average of the loss over the network. And if we minimize this average empirical loss, the quadratic fitting function that we are going to get will actually look like this. Okay, so a few assumptions on our problems, on the problem that we're interested in. So for the loss function, we assume this part is a smooth function. It can be either convex or non-convex, and the gradient of the loss function can be unbounded. And some of the simple examples, say for example, a linear regression problem, we want to our prediction function is a linear transform of the input feature, and in an example of the loss function can be the simple least squares loss that I just introduced before. And another example would be a classification task where our prediction will be a linear transform, still a linear transform of the input feature. And we can assign different loss functions for classification problems, such as the 0, 0, 1 loss function, which says that if our prediction has the same sign as the label, then the penalty or the loss is equal to 0. But if the sign is different, then the penalty is equal to 1. But however, we can see that this loss function is a discontinuous function in terms of the variable, and therefore from an optimization perspective or training perspective, it's hard to optimize. So in practice, what we can do is to approximate this 0, 1 discontinuous function by a continuous function, and that gives us some commonly seen classifiers, such as the SVM classifier that corresponds to this hinge loss, and the logistic regression loss function that corresponds to this smooth curve. Okay, and another, so up till now, all these loss functions that I introduced are actually convex functions. So what about the examples of non-convex functions? A very typical example is a neural network function that can be represented as this composite function. And here this function can be represented as a graph where we have the nodes represents the nonlinear activation functions, and we have the edges represents the linear transform. And this function is just the composite of the linear and nonlinear transforms, and this function is clearly highly non-convex. Okay, so much about the examples of loss functions. Now, what about the regularizers? So as I mentioned before, for some of the applications, we would like certain structures on the parameters that we are learning, for example, sparsity. And in order to promote sparsity, an idealized penalty or regularizer that we would like to employ is the L0 norm, which is basically the cardinality function. So it's equal to 0 when x is equal to 0, but when x is not equal to 0, it's equal to 1. So as before, this L0 norm is a discontinuous function, and it's difficult to optimize from an optimization perspective. So what we commonly do is try to replace it or approximate it by continuous functions, and a popular regularizer as an approximation of the L0 norm is the L1 norm that looks like this. And for the L1 norm has many desirable properties. Say, for example, it's convex, and in terms still from the optimization perspective, it will be easier to deal with. However, from the figure we can see here, the L1 norm is actually a crude approximation of the L0 norm. And as x gets larger, the discrepancy between the L1 norm and L0 norm gets larger. So in order to fix this issue, people propose to improve the L1 approximation by some of the non-convex surrogates of the L0 norm. So, and they basically look like this. So they're like this butterfly shaped. And we can see from the figure that they better approximates the shape of the L0 norm. However, as a trade-off, we can also see that convexity is sacrificed here. So all this better approximation of the L0 norm, they are non-convex. So statistically, they may enjoy a better property in terms of promoting sparsity, but from the computational perspective, they are putting more difficulties in terms of the training or the optimization procedure. And it has been proved recently that for this class of non-convex regularizers, they have a very desirable or interesting property is that they can be written as a DC function. So a DC function is the difference of two convex functions. And for this family of functions, we can have a better control in terms of computation. And in the rest of my talk, I'm going to assume that the regularizer is a DC function. Okay, so the last assumption that I'm going to talk about is the structure of the network. And in this talk, I focus on a fixed and undirected network. And what does that mean? So here, the model of the network, we will model the communication network among the agents as a fixed undirected graph that consists of nodes and edges. So the nodes here represents the agents, and the edges represents the communication link. And the communication link is undirected. So basically, it means that if say here, agent 1 can talk to agent 4, then 4 can also talk to agent 1. So the communication is bidirectional. And we call an agent agent L is a neighbor of agent I if there exists a communication link between these two agents. And also for simplicity, we also include each agent I itself as its neighbor. So in other words, this graph contains self loops. Okay, so a quick summary on the network structure. So our problem has the following properties. Because each of these agents, the data is scattered in the network, and each agent only knows its own portion of the data. Therefore, each agent I only knows its local loss function Li, but not the loss function belongs to the others, because this one depends on the data set of the others. And we're saying data cannot be moved around in the network. And each agent I can receive information from its immediate neighbors. So if there is a communication link between these two agents, then they can send information to each other. However, say, for example, here, there is no communication link, then the agents cannot talk to each other in one hop. And we assume a minimum assumption on the connectivity of the network, and that basically requires the graph G to be connected. And intuitively, that means that even if there is no direct communication link between two agents, then, but possibly through multiple hops, the information that belongs to one agent, say L here, can eventually reach any other agent in the network. Okay, so this is the setup of our decentralized setting. And in such a setting, we ask the following questions. First of all, can we design an algorithm, a decentralized algorithm, that is capable of solve this regularized empirical risk minimization over the network? And if there is such an algorithm, second question that we are interested in is that can we achieve the same convergence rate as that of a centralized algorithm? So does decentralization cause any loss in terms of learning or not? And the third question that we are interested in is that can we try to improve the convergence rate of the algorithm, leveraging the statistical properties of the problem? So put us in the context of a statistical learning problem. Okay, now let me start with the first question. So up till now, is there any question regarding the setup? Okay, nobody is speaking, so I assume that the setup is clear. Okay, so before I formally introduce our algorithm SONATA, let me try to briefly recap a classical algorithm that is the decentralized gradient descent that has been there for decades, and then I will point out its a shortcoming or the issue that DGD has, decentralized gradient descent algorithm has, and we will start our algorithm by fixing that, start introducing our algorithm by fixing that issue. So let me first simplify a bit our problem by dropping the constraint here and also delete the regularization term so that our loss function is a smooth loss function. And in order to solve this problem over a network, we face the following difficulties. First of all, each agent only knows its local loss function, but not the average loss function in the network. Therefore, each of these agents by itself cannot solve problem P. And second, this problem is coupled among the agent, and the optimization variable theta is the complicating or coupling variable. Now, in order to solve this issue, the idea is actually pretty simple. So since theta is a common variable and that's the coupling variable, so let's decouple the problem. And the way to do that is that we will create a local copy theta I for each agent I of the common variable theta. So note that theta I is a copy of the common variable theta, so they have the same dimension, and we assume theta is in RD, is D-dimensional. And now we have two objectives. First is optimality, and second, we need to force the local copies theta I to be equal to each other so that each of these agents will collaboratively solve problem P. And in order to achieve these two goals, the algorithm basically does the following two steps. First of all, it will employ a local optimization step that is a simple gradient step. So each of these agent I will move its local copy theta I along the gradient direction of its own local loss function with a step size gamma k to reach the next point. Now, however, as we said before, the data is scattered in the network, so each of these agents will observe different sets of data. So generally, their local loss function Li will be different from each other. And if we let the agent execute only a local optimization step by themselves, the local gradients will drive the points to different places. And as a result, we cannot solve the original empirical risk minimization problem P. So in order to address this issue, we will employ a so-called consensus step right after the local optimization step, and that takes the following form. So right after gradient descent step, the agent will average their local decision variables through weights Wij, and this Wij forms a convex combination of the decision variables. And because that's a convex combination, we can see that after this averaging procedure, the points will get closer to each other. So essentially, the consensus step is a step that is forcing the local copies to to be equal to each other iteratively. And the algorithm basically executes between these two steps and iterates until the iteration index k goes to infinity. Okay, so what about the property of this algorithm? What we can prove is that if the step size or learning rate we're employing here, gamma k, is decreasing, is diminishing to 0, then the algorithm will converge at a sublinear rate to the optimal solution if the problem P is a convex problem. And this is proved in 2009. And later on, this result has been enhanced 5 years ago. And in this work, basically they removed some of the assumptions here and then proved that the algorithm has a linear speed up and can outperform the centralized algorithm in terms of communication cost. Okay, so this is the scenario when we use a diminishing step size. Now, the question is, can we use a constant step size here in this algorithm? The result is actually negative in the sense that if we use a constant step size here and assume that this problem is a convex problem, then the algorithm can convert, is strongly convex, sorry. Then the algorithm can converge at a linear rate, but it will only converge to a neighborhood of the optimal solution of the problem. And the size of this neighborhood, epsilon, depends on the step size you are using. The larger the step size you use, the larger the epsilon neighborhood will be. And if you want to reduce the size of this neighborhood, then you have to reduce the step size. So essentially, there is a dilemma here. We know that if we employ a larger step size, the algorithm runs faster. However, it's more inaccurate because the neighborhood size is getting larger. But if we want the algorithm to be accurate, then sorry, we have to slow down the algorithm. And that's the issue with DGD. Now, the next question is, where is the deficiency in this algorithm that causes the problem with DGD? So the issue here is actually in the local optimization step, and I highlighted in the red color. So in this optimization problem, each of these agents is moving along its own gradient direction. And remember, our target is that we want each agent to solve the empirical risk minimization, where the objective function is the average loss function in the network. So essentially, ideally, the agents should employ a gradient step with the gradient direction that is equal to the average of the gradients in the loss function, but not the gradient of its own loss function. And because of the discrepancy between the correct descent direction it should use and the actual descent direction it's using, because there is an error here, and this error is not decreasing as our algorithm goes on. And this error is going to destroy the convergence of the algorithm, meaning that if we use a constant step size, we will never converge to an optimal solution of the problem. And if we want to kill this error, we will have to use a diminishing step size, and that basically kills the convergence rate of the algorithm. So this is essentially the issue with DGD. Now, having identified the issue, the next question is, how can we fix this issue? So the idea here is that instead of using the wrong descent direction, we will replace it by an estimate of the correct descent direction. And this estimate, and remember this gradient of the average loss function in the network that is not locally available to each of these agents. So we have to estimate this quantity iteratively using the network. And this is done as follows. And this is the so-called gradient tracking technique that is used pretty frequently nowadays. And it goes as follows. So for each of these agents, we will introduce an auxiliary variable that is called S I for each agent I, and this SI plays the role of estimating the average gradients in the network. It's initialized as its local gradient and updated according to this equation. So a quick explanation of this equation is that at each iteration, the agents will first subtract its previous gradient and then add a new gradient at the current iteration. And by doing so, the total sum of the gradient estimators in the network will be equal to the total sum of the gradients in the network. And then they perform a consensus or averaging procedure similar as this step. And the purpose of this averaging is to force the gradient estimators in the network to be equal to each other. And remember, we are just saying that the sum of this gradient will be the sum of these estimators will be equal to the sum of the gradients in the network. And if they are averaged out among the agents in the network, so we are hoping that each of these agents will get the average gradients in the network. That's the rationale behind this gradient tracking update. And what we can prove is that if we replace the wrong direction by this estimate and employ the gradient tracking step, then we can in this case, we can use a constant step size and the algorithm will converge. And this results in the convex setting are proved in the following works. But all of these works are assuming that the loss function is smooth. Now, the second question is how to deal with the constraints and the regularizers if we want to impose some structure on the solution. The solutions here is pretty straightforward now. So instead of using a gradient descent algorithm in the local optimization step, we will use the proximal gradient step in the local optimization step. However, note, as before, this quantity, which is the average of the gradients in the network, that is not locally available to agent I. So the way to deal with it is, as before, we will replace this quantity by the gradient estimator Si that we have just constructed. Okay, so that's how to deal with the constraint and regularizer. The next question is that note that a proximal gradient algorithm is actually a first order algorithm, and that is a kind of local linearization of the objective function. So the next question is that can we outperform a simple linearization scheme if we have more information on the objective function? And so the way to achieve that is the following. First of all, we will split S into two parts, where the first part is the gradient of the local loss function, and the second part is just the difference between Si and the gradient of Li. So after we do this splitting, let's put back these two quantities into the equation, and we can see that the objective function here in the local optimization can be split into two parts, where the first part is a linearization of Li, that is the local loss function belonging to agent I, plus a linear term that basically plays the role of estimating the loss function that belongs to the other agents that agent I does not know. And after observing this, we can see that we can, instead of just linearizing Li, which is known to agent I, we can replace it or generalize it by constructing a strongly convex function that is an approximation of Li and possibly better explore the information of Li that is known to agent I. Okay, so this is basically the complete picture of our algorithm SONATA, and looks complicated, but it consists of essentially 3 steps. So first of all, it is a local optimization step performed locally at each agent I site by solving this a strongly convex approximation of the original problem P. And second, in order to force the local copies to be equal to each other, we are employing a communication step that is averaging the local copies among the network. And the last step of our algorithm is a gradient tracking step that essentially tries to estimate the gradients using communication in the network. And this information is going to fit into the next round of the local descent step in this term. And what we can prove is, okay, first of all, I need to introduce the merge function of the algorithm, that is m theta k, and that is basically measures the distance of my points from stationarity as well as the consensus error. So when mk is equal to 0, that means all of the local copies of my algorithm will reach a stationary point, and they are going to be equal to each other. Okay, so what we can prove is that our algorithm can employ a constant step size, and when the loss function or when the problem P is strongly convex, the algorithm can converge at a linear rate if the step size is sufficiently small. And in the general case, when the problem P is non-convex but has a smooth composite non-convex form, meaning that is the summation of a smooth function and a non-smooth convex function, then we can show that a stationary point is reached at most 1/epsilon iterations. This is the typical sublinear convergence rate of an algorithm for a non-convex problem. And this algorithm can also be generalized to a time-varying directed graph, which I don't have time to talk about in detail now. And here is a simulation of the performance of the algorithm. So the problem we consider here is pretty simple. It's actually a sparse least squares problem. So each of these agents is taking linear measurements of a ground truth signal, theta star, with some observation noise Wi, and we would like to estimate the ground truth by minimizing the least squares loss over all the data in the network. And in order to promote sparsity, we're employing here a DC regularizer, and I think in this simulation, we're using the LP norm here. So the plot I show here is the number of message exchanges, basically the iteration of the algorithm, versus the distance of the points from optimality, that is J theta k, and also the consensus error of the local copies. And remember, when these two criteria, when they drop to 0, that means both optimality and the consensus are reached. And this figure shows the performance of a distributed gradient algorithm, and indeed what we can see here is that this algorithm performs quite slowly because it has to use a diminishing step size and the rate is sublinear. And by using the gradient tracking technique, we can fix this issue, and this is the performance of our algorithm that is a linearly convergent algorithm, and it's significantly faster than the DGD, distributed gradient descent algorithm. Okay, so here the result here is a general result, meaning that we are not given a very specific characterization of the surrogate function. As long as it's strongly convex, then we can prove the convergence result like this. Now, what if we choose the surrogate function to take some of the specific form? Say, for example, what if it's just a very simple linearization of the local loss function? So in this case, we can particularize this theorem to the linearized choice. And what we can obtain is that if we choose the surrogate to be a simple linearization of the local loss function, we can show when the optimization problem we're considered here, if it's a strongly convex and smooth L-smooth problem, then the algorithm converges at a linear rate with coefficient L over mu here. And this is the condition number of the problem if the network is sufficiently connected. So rho here characterizes the connectivity of the network. And if rho is sufficiently small, that means the network is sufficiently connected. Now, how to achieve this requirement? We can do so by running multiple rounds of consensus step per computation iteration. And if we do so, that will give us a communication complexity of the algorithm that is kappa, the condition number of the problem, divided by square root 1 over rho multiplied by log 1 over epsilon. Still is a linear rate algorithm. And from this result, we can see that the order of the convergence of the algorithm actually matches the convergence rate of a centralized gradient descent algorithm. And in this sense, we answered our first question. So in terms of the performance of the algorithm, decentralization does no harm compared to its centralized counterpart. The next questions that we are interested in would be, can we outperform linearization if we have some desirable properties of Li, the local loss function that we would like to use? So can we speed up the algorithm? And how can we choose the surrogate function to leverage this information? And in order to answer this question, I need to we need to put ourselves into the context of a empirical risk minimization problem. So, so the next part that I'm going to introduce is that how can we choose the surrogate function in order to leverage the statistical property of the problem? And remember that we are dealing with a empirical risk minimization problem. So each of these agent I will have an average loss function over their local data set. And a very simple but useful observation made around 10 years ago was that if the local data sets are in IID distributed, then the local loss functions at each agent's size will be approximately equal to each other, and they will be approximately equal to the average loss function in the network, because eventually, if the data size, as the data size grows, all of them are estimating the expected loss function over the entire data distribution. And by using this observation, what we can do is that we can choose the surrogate function that takes the following form. So how does it, so it has the structure looks like this. So the motivation is that because our local loss function is close to the global loss function, that is the average of the loss function in the network. So instead of simply linearizing my local loss function, actually I can just use it as my local objective because it's already close to the objective function that I would like to optimize. However, I'm adding a correction term to the local loss function in terms of its first order information. And this correction term basically fixes the gradient of my local loss function. So here we can see that we are subtracting the gradient of the local loss at a current iteration, but adding the gradient of the global loss function. And in this case, we are basically fixing the first order optimality condition of the problem so that to avoid the speed accuracy dilemma that we just talked about for the DGD problem. And also, I need to remind you that we're in the decentralized setting, so this average gradient information is not available to each agent I, and as before, we need to replace it by the gradient estimator that we just constructed using the gradient tracking technique. And that gives us the local optimization step looks like this. So in particular, it consists of two parts. The first part is essentially the local loss function of agent I itself plus a quadratic term to make it strongly convex. And the second term plays the role of estimating the missing information of the loss function corresponds to other agents in the network. Okay, so this is how we construct the local optimization problem using surrogation. Now, what about the convergence property of the algorithm? What we can prove is that suppose our local loss function is close to the global loss function in the sense that the Hessian of these two objectives are bounded by a constant beta, then what we can show is that if the problem is strongly convex and L smooth, the algorithm will converge at a linear rate, and the coefficient here will be equal to beta over mu if the network is sufficiently connected. And as before, to meet this criteria, we can run multiple rounds of communication per computation step, and that gives us a communication complexity looks like this. Okay, now let's make a quick comparison of this convergence result to its counterpart, where we're just linearizing the local loss function. And this is a quick recall of the convergence result if we use a linear surrogate function. And we can see that if we linearize the local loss function, then the complexity result depends on the condition number of the problem, that is L divided by mu. However, if we use the statistical preconditioned surrogate function that I just introduced before, then the coefficient here becomes beta over mu, where beta measures the mismatch between the local loss and the global loss. So if we do this comparison, then we can see that we can outperform linearization under the condition that beta is less than or equal to L. All right, now here is some simulation validation that compares the performance of the simple linearization scheme and the statistically preconditioned surrogation choice. And what I'm plotting here is that when we use the linearization scheme in the local optimization step, what we can show is that, okay, let me first explain this panel. And the x-axis is the condition number of the problem. And the y-axis here is the number of iterations for my algorithm to reach an epsilon accuracy of the optimal solution. And we're here considering a least squares problem because for this problem, we can better control these parameters like kappa and beta. And as we can see, if we use a linear surrogate, and if we increase the condition number kappa of the problem, then the complexity of the algorithm increases as kappa increases. And this part of the curve actually corresponds to the situation when the network is not satisfying this connectivity condition. Okay, now the next panel of the problem of this figure shows that the first one shows that if we increase kappa, then the algorithm complexity scales linearly with respect to the condition number. The second one shows that if we fix kappa, but increase beta over mu, increase the dissimilarity between the local loss function and the average loss function. In this case, the linearization scheme is not sensitive to kappa in the sense that the iteration complexity stays roughly constant. Now, what about the performance of a statistical precondition surrogate? It's actually the other way around. So here, still we are increasing the condition number of the problem, but fixing the similarity between the local loss and the global loss. And in this case, we can see that if we choose the statistically preconditioned surrogate, the algorithm's complexity is not sensitive to the choice of kappa, in the sense that the complexity stays roughly constant. However, if we fix kappa but increase the dissimilarity, then the algorithm will deteriorate as the local loss and the global loss becomes less and less similar to each other. Okay, now the final question. When shall we choose linearization and when shall we choose surrogation? So the answer to this question is pretty obvious now. And this figure basically shows under what scenario shall we choose a statistically preconditioned surrogate. The answer is that when beta over mu is less than L over mu, then let's choose a statistical preconditioned surrogate. Otherwise, let's use linearization. Okay, so when will beta over mu be smaller than L over mu? In some of the empirical risk minimization problems, that is the case. And here is one of the examples that is called the regularized empirical risk minimization problem, where we have the loss function that is merely convex, not strongly convex, and is regularized with the regularization term equal to the quadratic. That is a simple quadratic function in terms of the optimization variable. And in this setup, what we can prove is that the condition number of this problem is of this order, that is the square root of d, that is the dimension of the problem, multiplied by m, that is the size of the network, and small n is the local sample size. However, beta over mu for this problem is of order square root d multiplied by m. So from this formula, we can see that beta over mu is always smaller than kappa for this example. And another desirable property we can see that is that beta over mu is independent from the local sample size. And that means if you increase the local sample size, and if we use a statistical preconditioned surrogate, the complexity of the algorithm is not going to change. But if we use linearization, then the complexity is going to deteriorate as we increase the local sample size. And that is the advantage provided by statistical preconditioning. Okay, so some conclusion up till now. We have proved that if we leverage the gradient tracking technique, we can overcome the speed accuracy dilemma of the DGD algorithm, in the sense that we can choose a constant step size now, and for strongly convex problem, the algorithm can converge at a linear rate. And if the problem is convex or it's a structured non-convex problem, then the algorithm can converge at a sublinear rate. And we also show that for some statistical learning problems, we can try to properly choose the form of the loss of the surrogate function, and in this case, that can help to speed up the convergence rate of the algorithm. May I ask how much time is left?
Maybe 2 minutes.
Okay, 2 minutes, then probably I will just cut my talk here and leave the rest of the time to the audience. So without talking about this high dimensional setting.
Okay. Okay, thanks for the nice talk.